Hi, my name is Zainab Gilani, and I'm an Energy and Power Associate with Cleantech Group. So as an Energy and Power Associate, I cover a really wide variety of sectors. I've been researching topics in energy storage, novel battery chemistry, thermal energy storage, mechanical, and I also look at a variety of power generation technologies, so geothermal, nuclear fission, nuclear fusion, and we also look at different areas of grid tech, data centers, and other strategies for decarbonization. We released our Global Cleantech 100 report a few weeks ago where we highlighted a few areas that we thought would see particular growth. Some of these areas include fusion, fission, geothermal, AI for grid, other related grid technologies, and various strategies for data center decarbonization. So I'm really excited to be joined today by Mac Hatch from MetOx. Mac, do you want to do a quick introduction?
Yes, I'm Mac Hatch from MetOx International. I'm the Vice President of Strategy, and MetOx manufactures high temperature superconducting wire, or HTS, which is used in fusion magnets to create the magnetic fields that create the fusion reaction, and also in cables for the grid or for data centers. An HTS cable can carry 5 to 10 times the amount of power through the existing right-of-way.
Yeah, and I'm really excited to be working with technology that's in this space because as we've been looking at this area, as we've seen particular areas of growth, and three main areas that I wanted to talk about include fusion, grid tech, and data centers. And luckily, high temperature superconductors have applications across all three. So Mac, I kind of just wanted to turn it back to you. Like, as you're thinking about the different markets, how are you thinking about the applications for high temperature superconductors in both fusion, grid tech, and also data centers?
Yeah, I'll separate those out into kind of two distinct categories. There's fusion and then the cabling space, both in the grid and in data centers. And fusion is really the accelerant, the ignition for the superconducting industry. The pilot reactors require anywhere between 15 to 20,000 kilometers of HTS wire, which has allowed the industry to scale up, and that's driven down the cost of HTS wire. And then that's enabled some of these other applications like the cabling space, where you are competing against traditional copper cables and you want to be economic. And then add data centers to the mix and electrification. And now you need to grow the capacity in the grid, you need to replace cables in the grid, just overall expand the grid. And that's really driven the interest in superconductors, which can carry a lot more energy through smaller right-of-ways.
In our Global Cleantech 100 report, we talked a little bit about how we're seeing particular growth in fusion. There was an incredible amount of investment in 2024, but even 2025, we saw companies like Commonwealth Fusion and Helion see particularly large rounds. Commonwealth Fusion raised over around $800 million. Can you talk a little bit about how the magnetic confinement technologies in fusion particularly need high temperature superconductors and maybe why they can't use other types of magnet technologies?
Yeah, and so the background behind a lot of these magnetic confinement fusion reactors is really around the eater design. So they use the same tokamak design as CFS or similar to CFS, but they use low temperature superconductors. Yeah. They're less energy dense and they're required to go down to around 4 Kelvin, close to absolute zero. And so this was fine for a global project where you have all the countries supporting it, but it's really expensive. And then high temperature superconductors cross the cost and production thresholds required to commercialize. And that's when CFS was able to raise their big round using a design that's more cost effective, smaller, and able to get to market economically.
Yeah, and we saw over $2 billion go into this space this past year. Can you talk a little bit about how, as the fusion industry sees more investment, what that means for technologies like yours in terms of just scaling production and maybe how costs might come down over time?
Yeah, and so a lot of this cost has been taken out of the HTS manufacturing. There's still room to improve, but it was because of fusion. So CFS had the first big round, and that led to something that was new to our industry, which was there were multi-year offtake agreements, which allows us as manufacturers to start scaling up production, getting those economies of scale and taking cost out of the system. And so really that first multi-year offtake was critical for our industry to start scaling it and reducing cost.
Great. So do you think fusion will be the biggest source for your customer base for the next 5 years? Or are you still thinking that other applications in other industries might, you might be looking to sell into those in parallel?
Yeah, I think fusion over the next 5 years is going to be the key driver with these pilot reactors. There's about 50 odd fusion companies, about half of them are magnetic confinement, and they all are going to need lots of HTS wire to scale up their pilot reactors. But close behind is cabling, the data center space, as they scale up to megawatt level power needs on the rack. They're going to need new solutions like superconductors.
Another key area that we highlighted in our Global Cleantech 100 report was the area of grid tech. We saw quite a number of investments in this space, and a number of the companies on our Global Cleantech 100 were actually operating in this space as well. Some of them include Ver, Ionate, DG Matrix, all kind of in the hardware space. Can you talk a little bit about how your technology also kind of fits into this hardware component that could also potentially improve transmission capacity for utilities, and what the kind of impacts on the grid high temperature superconducting cables might have in the future?
Yeah, so we believe that to solve the transmission problem, you're going to need all technologies. There's going to be software solutions, hardware solutions, but you're not just going to tackle it with software. You need to expand the grid, you need to expand the physical capacity of the grid, and that's where superconductors come into play. So a high temperature superconducting cable carries about 5 to 10 times the amount of power through the same cable size. And so if you're thinking about projects that we've seen with superconductors, like reconductoring a train station in Paris that wants to power more trains using they're out of conduit space, so they used a high temperature superconducting cable. Or in Munich, they want to connect one side of Munich to the other with their grid. These are underground cables, so you can either have 10 underground cables or 2 HTS cables connecting the city. And so where you see superconducting cables being more economic is when infrastructure costs are really high and the conductor cost itself is really low. And then superconductors oftentimes are the better solution.
As we're kind of talking about the grid infrastructure, there's multiple problems. One is that there's an aging infrastructure, and then there's also these kinds of different sources of load growth where energy is going to have to be transmitted to areas where maybe the generation doesn't exist there. Can you talk a little bit about how, as we're seeing an increase in data centers and power consumption from those users, what that means, A, in terms of getting the energy transmitted to those users, but also maybe making the energy infrastructure at the data centers more efficient as well?
Yeah, so I think for this one, it all starts with the planning. So you want to build a new area of the grid, and you estimate that it's going to require X amount of power. But you start building this cable, and a transmission cable can often take around 10 years from first design to getting implemented in the grid. Historically, that was fine because we had pretty stagnant load growth, but now we have a rapidly growing power needs in the grid, mostly because of data centers. And so you're starting to plan out 10 years, but also future-proof this for not 10 years, but these cables should have a 30-year life. And so now you're thinking 40 years out in the grid when you're building these cables. And that creates a unique challenge, and you want to think through how much extra capacity you need, not just how you're going to get power today, but power 40 years from now to these areas in the grid.
And so what is the specific product that you might be selling into data centers, and how might those product specifications be different from the other applications?
Yeah, so we just create the HTS wire, but we'll sell to our cabling partners, and they will sell into data centers. But when we think about data centers, there's really 3 key use cases of HTS. It's getting from the grid to the data center itself, and then it's moving power around the data center, and then it's connecting the rack level to the overall power system using a superconducting busbar. And one of the benefits that superconductors have is we don't have resistance. And so for copper, you bring it in at high voltages, you step it down because you need it at low voltages at the rack. And you don't have that issue with superconductors, so you can bring it all the way through the system at lower voltages, increasing permitting times and things like that.
Yeah, and I know the speed to scale is critically important. So as we're thinking about like the data center of the future, how do you think that superconductors will kind of be integrated at all aspects of the data center?
Yeah, so I think the first and main one is going to be within the data center itself, the bus bar connecting the rack level. The power demands right now are growing enormously at the rack. So you have something the size of a fridge that needs a megawatt of power. Well, our entire manufacturing plant takes a megawatt. So you're putting that in a very small space, and to have enough copper to get that power there without losing the energy, I think superconductors are going to be a much better solution there.
Yeah, and then can you talk a little bit about just like the space constraints that data centers have, and if you use superconductors, like does that open up more floor space for more servers?
Yes, typically the space is above the racks, so I don't know if you're going to get more servers, but you're running into weight issues with the copper, space issues overhead, moving the copper around, because you also have the cooling systems there. And so there are some constraints that you have to work with. And with copper, you have the heat loss from the resistance in the copper. And you have to take that heat out of the system. You don't have that issue with superconductors.